It's a great pleasure to speak here. It's my first time presenting this result that hasn't been posted to market, but hopefully will come out soon. So it's about multi-time distributions of inhomogeneous TASEP depending on two sets of parameters. So what are the models we are studying? It's just the usual TASEP, but we will introduce two sets of parameters following. This is following the notation of Bording and Pichet when they introduced this model. So you have the usual TASEP, but it's more convenient to view instead of particle and empty sites, you view it as black or white particle, where the ordering for the black particle is from right to left, and for the white particles from left to right. And each of them carry a parameter, pi I, either pi I or pi I hat, depending on whether it's black or white. And when the ith black particle meets the j's white particle, they will exchange their location after an exponential pi plus pi j hat waiting time. That's the model, very simple. And equivalently, this is maybe more familiar in the other type of format, interpreted as a exponential loss passive percolation model, where you consider the usual maximizing over the upright path from 1 to some other location mn, but here the ij site has an exponential waiting time with parameter with rate pi plus pi j hat. And under the standard coupling between TASEP and exponential loss path percolation, there is this this equality in distribution where basically the joint distribution of particles is translated to the joint distribution of loss path time. So that's the model, very simple, and there's maybe almost everything's known for this model except the thing I'm discussing today. So this model in this generality is introduced in 2007 by Bording and Pichet, and it is well known that the 1-point marginal of the loss passage time. So if you consider a single loss passage time, the distribution is distributed the same as some largest eigenvalue of some complex B-sharp matrices, and it is essentially Schur measure, of course, a continuous deformation of it, depending on two sets of parameters. And there are also manageable formulas for the equal time multi-point joint distribution, where it's still some Fredholm determinism. So that's for the, what should I say, the algebraic part. For the asymptotic parts, assuming there are only finite many, sorry, there's a typo here. So it should be 1 instead of 0. So assuming all but finite many pi's are 0 and pi j's hats are 1, then you are only consider a few columns or rows that are not of uniform rate. That's some kind of finite rank external source if you want. Then the limiting height fluctuations exhibit the famous Baik-Ben Arous-P shape height phase transition, where if the external source has a rate that's above some threshold, then everything is the same as uniform. If it's below the threshold, then basically the fluctuations are governed by random walks on this finite, what should I say, random walks on this finite direct source, so you get some Gaussian type fluctuation. And when this rates are around that critical level, you can scale it in an order of t to the negative third, and then what should I say? There's some interpolating distributions known as Baik-Ben Arous-P type, or rather, in these two sets of parameters, it's introduced first by Bording and Pichet. So a particular case is when you basically you put either one side or one row and column with critical rates, then those things are related to TASEP start with Bernoulli initial data or two-sided Bernoulli initial data. So that's basically the models here. And today, what I'm going to talk about is the arbitrary many space-time joint distributions and some formula for it. It's going to be technical because the formula is complicated, but to me, it's fine. It's at least understandable in my opinion, but hopefully to this audience, uh, I don't need to explain to spend infinite time explaining it. So what are the object I would like to study? The object would like to study is the following joint distributions. I write it in terms of several tech particles. One can easily translate to the joint distribution of several of the last passage time at several space-time location, or the joint height joint distribution of the height function. So that's the object I'm going to discuss today, and this is something not that well studied, or just studied to be understood. So along this direction, so the first mathematical rigorous work is by Johansson in 2015 for a two-time distribution of Brownian last pass percolation, I think. There, the formula is really complicated. It's some very complicated series formula, I think. Uh, to me, the first understandable or the first general result is obtained by Baik and Liu in 2017. But instead of studying this usual TASEP on Z or last pass percolation on the first quadrant, what they study is a periodic or ring version of the TASEP, where particles essentially move on a circle instead of on the infinite lattice. And that's maybe some of the motivation for this one basically comes from their work. And it's a kind of a surprising fact that the ring version in computing the multi-time distribution, the ring version is easier. And for the infinite TASEP, there are basically two results that come about the same time by Johansson-Rahman, by Liao, study basically slightly different versions. One for the geometric loss path percolation, and the other for the exponential loss path percolation or TASEP. But I want to point out the formulas. These two formulas are quite different formulas. They are what should I say? Very similar in spirit. Both of them are expressed as counter integrals of Fredholm determinant, but the two Fredholm determinants live on different spaces. And a priori, at least I don't know how to verify the two Fredholm determinants are identical up to some conjugation. There's no clear simple conjugations at this multi-time level. But I made some effort trying to see that, and I believe they are the same. So I have some previous work following the roots of Liu, first studying the of Baik and Liu, of first studying some periodic model, and there I studied some discrete time TASEP, periodic discrete time TASEP, and then from there one can obtain some formula for the multi-time distribution of geometric loss path calculation. They are the same thing basically. But I'm not going to talk about that in detail today. So today I'll mostly focus on a continuous time TASEP or exponential loss path calculation, but with two sets of parameters here. Along this direction, there are some very recent work by Johansson-Rahman again. Actually, I don't know that they are also doing that when I was doing this. But anyway, the results are parallel and not fully covered by theirs, so it's fine for me. So what they did is they computed the two-time distribution of some inhomogeneous geometric last path percolation. they have some formula that involve two sets of parameters, but ultimately their formula only they only carried out the calculation for one set of parameters, essentially either the row or the column, and for two time basically. So today I'm going to what I'm going to talk about is the multi-time version of this. So here is the main result. It may take me a lot of pages to describe it, but this is essentially what it is. So one consider the a inhomogeneous TASEP with the two sets of parameters pi and pi j hat. I just want to remind you. Basically correspond to introducing different jumping rates for different particles and empty sites essentially. And here for presentation reason, I'm sticking to the step initial data, xi 0 equals -I. This finite time formula works for general initial condition without too much modification of the formula. So then this space-time joint distribution. Here I'm assuming T1 is less than or equal to T2, less than or equal to Tn. I'm fixing M arbitrary space-time points. Here they can be equal. It's when you take limits, you need to assume they are strictly ordered. Otherwise, the kernel diverges. So there is some extra message if you consider equal time, and if at that time I expect this formula reduces to the familiar extended area type kernel when you do some massage of this formula. But I will not I did not try to work hard to work that out. Here, what's the formula look like? The formula is the following. You have a joint distribution, and it's actually an m-1 fold contour integral. Here, there are m-1 parameters here, theta 1 through theta m-1, and this is a m-1 fold contour integral, where the integrand has two parts. One part is simple, it's simply this product of this m-1 factor. The other part, d, which I didn't give you the precise definition of it yet, but it is a Fredholm determinant. And this theta enters this Fredholm determinant in some very minor way, but essentially some multiplicative factor into this Fredholm determinant. But it makes this Fredholm determinant a function of these parameters theta 1 through theta m-1. And the final, what should I say, m time distribution is given by the contour integrals of this over circles of radius less than 1. They are not necessarily nested. So for the theta 1 to theta m-1. So essentially, once picking up the residues in terms of the theta 1 to theta m of the integrand, essentially. So basically, this I stated for step initial condition. The same formula works for general initial condition with very minor modification of this Fredholm determinant part. One only need to change at one position of the kernel of this Fredholm determinant. So that's the structure. It's to be expected because basically the conditional law of any say if you consider endpoints and you fix the first one, then the conditional law of the remaining things doesn't depend on the initial data, essentially. So what is this D part? This it's a very complicated thing, but I hope it's understandable. It takes very similar structure, or not that similar, but more or less same as the one-time case. So it acts on some disjoint unions of several contours, usually seen in this inhomogeneous in TASEP. You have So for endpoint, for the m time distribution, you have essentially 2m minus 1 contours or 2 times that contours. So what are those contours? You have here the contours are there are two. I divide. What should I say? How should I describe this from scratch? So I first they are I divide the sets of all contours into two subsets, which I call S1 and S2. Basically, the union of them are the all the contours that I'm considering here. And what are those contours? Those contours are shown in this picture, where essentially one have two sets of contours nested, and it's nested in the following way. Say, because I have what should I say? Because I have two sets of parameters, pi j and pi l hat, and I'm assuming there's some, sorry, this should be negative of pi l hat, another typo. So I'm assuming that their sum is positive so that the radius is not going to be a negative number. And then basically the rates naturally splits into two parts. One I call the left part, and the other part I call the right part. And then what's happening is one take count two sets of contours, the left contours and the right contours, where the left contours only winds those left poles, negative pi l hat, and the right contours only winds those right poles, pi j. And these two sets of contours do not intersect. And then for each set of either left and right contours, there are 2m minus 1 of them. And uh, they are nested in the following way. So one first picks a simple a single contour that I call sigma 1l that winds around the left poles, and then I'm going inwards and call the other guys sigma 2l minus, sigma 3l minus essentially. And I'm going outwards, and the other one is reversed. I call it sigma 1 plus and sigma 2 plus and sigma 3 plus, so and so forth. So the left contours essentially are sigma 1 L, sigma 2 L plus minus, sigma 3 L plus minus, that going all up to sigma L M L plus or minus. So if you counted this, there are 2m minus 1 of them. Of course, one can introduce a sigma 1 plus or minus, but because one can deform them together, so there's no need to introduce two contours for sigma 1. And the same is for the right contours as well. And then basically S1 and S2 are some half of the unions of this contour, where in this graph, in this picture, essentially the blue contours are S1, that's the underlying space of this Fredholm determinant, and the red contours are the other part. So this space actually doesn't depend on the actual parameter sigma, but we will introduce some dependence on the actual parameter theta, but we introduce the dependence here by putting some kind of complex measures on these contours. One can put this what should I say, this parameters into the kernel, but this is the most natural way to me to 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 associate those parameters sigma to the kernel. That is, we put it inside the underlying space, and the way it's not that complicated, but it's mysterious in some sense. So what we do in the what should I say, in the first contour sigma 1 L and sigma 1 R, we simply associate to the normalized Lebesgue measure, essentially. In all the other things, we put this parameter negative theta over 1 minus theta to the plus contour, and we put this 1 over 1 minus theta to the weight to the negative contour. You can check, if you add these two, you get 1. So 1 is artificially split the, what should I say, the plus and the minus 1, And this kind of what should I say parameter is basically to encode the ordering nature of TASEP. So one reason why the periodic model is easier in this scenario than the infinite one is there is no ordering on the circle. So basically, there is a very similar formula first obtained for periodic one, where you don't need to have plus or minus. You what should I say? Nothing. You only need to have uh, m counter or not counter m set of roots instead of this two m minus one, two m minus one nested contours. But essentially, there are generalizations of the single time distribution. If you are familiar with the single time distribution, which I will remind in maybe a few minutes, it consists of one left contour and one right contour essentially. Then that's the underlying space. It took me 5 minutes to explain this already. Then the kernel. The kernel is also not that complicated essentially. To me, it's basically a product of two operators. One going from, sorry, there are infinite amount of titles. This is S1, this is S2, whatever. One goes from S1 to S2 and the other goes from S2 to S1. And if you multiply them, you get an operator going from L to S1 to L to S1. That is the blue the L2 space living on this blue those blue contours. What happens? What is the kernel? The kernel more or less just is more or less similar to what to expect to see in the one point case, but there are extra interaction in the one point case. You only have the interaction between the left and the right contour essentially. So it's a scalar kernel. And in the multi-time case, what's happening is what should I say left contour sigma IL will not only interact with sigma IR, which is on the right, and also it will interact with the contour on the left that's neighbor to it. So there are interactions between these two the contours and also the counterpart, something like this. So if you really write down what the kernel is, it's a matrix kernel with block diagonal structure, and it basically consists of this fundamental block of 2x2 interactions. So basically, the only interactions with index that differ by at most one. That's the thing. And this is an example where you have a m equals 3, and there's two kernels, k1 and k2, are more or less given by this this 2x2 and then one 2x2. And this fundamental block 2x2 block is given in the following way. It's not that complicated. You can see it's actually appearing, what should I say, in a similar form as the one time case. It's given by the following. You have this kind of a Cauchy type matrix. Basically, this Cauchy factor is everywhere in computation. And then the essential weight function that encodes the what should I say inhomogeneity is given here. So it's basically if you are living in the left, there you take the a fj divided by fj minus one. If you're on the right, then you take fj divided by fj plus one, where this fj is this uh, familiar function if you look at Schur measure essentially. So then there is some dependence on this extra parameter theta, and it is entering with this kind of not that harmful scalar matrix essentially. Here to for the top left or bottom right corners, one need to make the really fit this general framework that there's this extra extra definition, just to extra convention, so that everything works nicely. But essentially, it is just a what should I say, block uh, matrix kernel with basically 2 by 2 blocks on the main diagonals. Essentially says basically the only interactions between left and right counters with the same index or counters that have index differ by 1. So of course it's already very complicated, but here is somehow, to me it's simpler, but to most people I think this is a more complicated formula. But at least it fits into one page after our yes question. uh, there's an equivalent series expansion of everything, but it takes four five column, no for 5 rows to describe it. But it's actually it says this Fredholm determinant you can run the usual series expansion for the Fredholm determinant, and it's written in the following. To me, it's more symmetric like it's the left and the right comes in exactly the same format, where you have this series summation where you summing over all multi-index with length m, and each of these term dn step is given by the following quite long multiple counter integrals, where this thing we just is just the complex weights we associate to those contours. So you just view them as this absorbed into this in this measure. And then the Integrand is something I would like to explain for a little bit. It's actually very simple if you want. This delta U is the usual van der Waals, so it's product uj minus ui I less than j or whatever. Of course, this if you assume your u equals to this vector, of course this thing depends on the what should I say the way you choose the ordering, but if you square it, it doesn't depend on the way you choose the ordering. And this FLU is basically a shorthand notation of product U in U FLU for any set U and V. All of the remaining things are self-explained essentially. This cross delta is basically you do the product UV in UV, something like that. Anyway, this formula to me is nicer because it's very symmetric and it's not that complicated actually. That's what this formula is. It took me about 15 minutes to explain it, but that's it. But at this moment, it's there's no what should I say? Uh, no one get any sense of what this hell really is. So here is a sanity check of what's happening, but maybe it's oversimplified. So let's take the single time m equals 1 just to get a sense. So for m equals 1, if you go back, this formula is written as an m minus 1 fold counter integral with respect to some parameter theta. So when m equals 1, there's no this outer counter integral essentially. And the only thing survives is the inner Fredholm determinant. And it actually reads like this. You are you are taking the Fredholm determinant of a kernel acting on the left contour, and the kernel actually look like this. Something might be familiar to some of you, some of you guys, but what's more commonly written in the literature is after a conjugation, you can change the underlying space, basically some AB determine 1 plus AB equals determine 1 plus BA stuff. You can write it as a kernel acting on, say, this is a finite K by K matrix actually, with this double counter integral kernel. That's essentially the double counter integral for the collision kernel of Schur measure. So really, saying that although our kernels does not look like something familiar, it's actually in conjugation to something that's very commonly seen in the literature. And it's really for the multi-time distribution, we really believe this representation using those counters instead of the what should I say, fixing it as the real line or maybe some part of some matrix. It's more convenient because what should I say, uh, it basically is more symmetric in the sense that it encodes the left and the right nature. So that's for the finite time distribution. And what let me the other part of the main result is about large time asymptotics. So let me briefly remind what's the BBP transition at single time. So what it states is that the height fluctuations are crucially affected by if you introduce some finite rank inhomogeneity to your model. So there is a critical threshold gamma depending on what location asymptotically you are looking at height functions actually. So depending on which, there are three different scenarios for the height fluctuations. The first is when basically your rate is below the threshold. That's a subcritical case when basically your pi I is more or less close to 0 and your pi j hat is close to 1. So then basically everything behaves the same as the homogeneous version, which is already obtained in the work of Liao, basically, for the multi-time case. For the single time, the fluctuation is known to be the GE trace-freedom law. And the other case is when you have a super critical case, which is you have several slow particles that have a rate slower than the critical value, negative gamma. Then what's happened is basically the fluctuations are governed by those last paths that stays at the first few rows in the environment. So it's basically some independent sum and some Gaussian type fluctuations. And the crossover between these two is when your pi is around the critical value with the window t to the negative third. Then we'll have the same KBZ scaling 1, 2, 3, but the fluctuations are described by some finite rank perturbation of the GUE trace-rhythm law, known as the Baik-Ben Arous-P law, or with two sets of parameters, it's really should be called Borodin-Pichet law. But I haven't heard this be called in this way. So anyway, that's just what's happening in this single time case, and exactly the same thing can be described at multi-time level. So we assume the same thing that is this pi I are equal to 0 and pi j hat are equal to 1 for all but finite many ij's. And then we assume at this, what should I say, at this talk that we're only looking at the last passage time at some strict diagonal. That is the row and the column has ratio going to 1 essentially. So that in that case, the critical value gamma is a half. In general, one can assume the limit ratio go to some any non-zero any positive number, and then the critical value changes, but just for presentation reason, I'll make gamma a half. And then what's the asymptotic result I would like to present? It's the following. First, I present the critical case. It's the most interesting case. I'm assume there are maybe R or S columns and rows that has a critical rate which is scaled around either negative a half or a half with a window of order t to the negative third, and there are these rescaled parameters lambda and mu. Again, because one wants pi I hat, pi plus pi j hat to be positive, one needs lambda I to be bigger than those lambda j's. And then under this scaling, the height fluctuations after the 1 to 3 kpz scaling will converge to something. So here there are parameters tau, gamma, and u, basically. So the tau are rescale time parameter, the gamma are rescale spatial parameter, and the two are those the number you plug into your distribution function. So this is some limiting distribution, and it has a almost identical distribution as its finite time counterpart. So let me briefly remind you what it is. So essentially, the formula takes exactly the same form. It's a n-fold counter integrals. Like this, with a different Fredholm determinant part D essentially. And that Fredholm determinant part has exactly the same structure as before, except you change the underlying space and you change the weight functions appearing in the kernel. So you replace the originally the e to the tw, you replace this thing, you replace this function by the area type function with a finite rank perturbation, which is of the form something like this. This rate function can say encodes the time parameter tau, the spatial parameter gamma, and basically the parameter u depending describing the fluctuations essentially. And there is this finite rank rational factor correspond to you are doing some deformation of it. And the integral contours change to this familiar contours for every function essentially, but with the same type of nesting. You should understand the nesting with respect to infinity. That is, you have parameter lambda j and mu j that are ordered in this way. Mu j's are viewed as the left poles and lambda j's are viewed as the right poles essentially. And then you have the two m minus one left contours and two m minus one plus contours with the same nesting. So one should really understand this contour as basically you zoom in some point here, and you basically look at the steep descent path for either the left or right contours near the critical point. That's really something familiar. And the asymptotic analysis is essentially very, very straightforward. So that's for the critical case, what's happening. The subcritical case essentially described before, it's the same as the homogeneous one, but what's happening is when one made the minor modification by basically setting this guy to be one, then one get the area type Fourier mode, and that's really uh, everything remains the same. And briefly, what should I say, discuss the supercritical case, which you expect to see some Gaussian fluctuation. And what happens is you just essentially you see Brownian motion, because all the fluctuations come from if you assume rank one, then after the scaling, what's happening is all the fluctuations of different time location for the last passage time basically comes from those part of independent sums of those geometric random variables, those exponential random variables at the first rule. So if you look at time t1, t2, then you basically add this many of, you basically pick up this part of the Brownian motion and so on and so forth. So really, it's kind of very easy to understand why one expect to see this the joint loss is given by the joint loss of Brownian motion at a different time location. So this can be obtained from the formula I just shown you, but in a kind of very hard and unpleasant way. I spent a lot of time trying to work this out, because in this regime you need to deform the contour significantly, and the main contributions come from those poles. In this case, the critical points naturally you need does not what should I say one in order to deform to the critical point, one need to pass some pole. So after I figured this out myself, I found that it's actually already been done in the literature. So that's kind of a little bit annoying to me, but it's already essentially carried through in this supercritical case by the work of Cohen, Ferrari, and Pichet. They did this without a explicit formula for the finite time multi-time distribution. And what they're doing is basically they are doing the thing I just described. They are using a probabilistic argument saying that disjoint fluctuations is basically given by the fluctuations coming from the past staying the time when the past staying at the first row column, something like that. And that's for rank 1 case. For general rank K, I did not make the calculation explicit, but I expect it will just fluctuate like the joint lowering time of a K by K Hermitian Dyson Brownian motion, essentially. Or maybe more intuitively, it's like you are running a Brownian lost path percolation with only K levels, and then you are looking at the fluctuation of the lost, the distribution of the lost path time at time location T1, tau 1, tau 2 through tau m, something like that. It's ultimately the fluctuation coming from the bulk are negligible. Questions or comments? So that's the main result. So I have time, so I can discuss some ideas of the proof. So the idea proof follows the idea of Liu essentially. Basically, it's really one start with what we call a periodic model instead of with a full space model. And in this case, the relevant model for us is the periodic TASEP, which is essentially the same TASEP dynamics, but your particles live on a circle or on a periodic domain with period L essentially. Everything remaining are the same. And the reason why I start with this, there are three main reasons for me. The first is the periodic ones are also interesting because they are kind of the interpolating dynamics between an infinite KPZ dynamics and some equilibrium dynamics. The other maybe more important reason is because in this multi-time calculation, the periodic models are easier. There are two reasons for it to be easier. One I just explained is because there is no ordering between particles. So some kind of summations are more natural to do in the periodic domain. And another reason is because due to this finite volume effect, the eigenvalues quantized. So you only have discrete, the problem is discrete in nature instead of continuous in nature. So as a result, the orthogonalization procedure is significantly easier. One do not need to use those fancy orthogonal polynomial techniques. It's actually when playing with finite matrices, something like that. So that's the comment I can give, and the whole procedure is summarized in the following diagram, which is something I have to explain a little bit. But essentially, it's the diagram look like this. So typically, what one do to obtain this kind of multi-time formula, or typically what one do to solve TASEP, is run through the four steps in the right-hand side, where one starts with some transition probability for the model in TASEP is the n-by-n determinant. This formula is due to Schur, basically. And then one perform a multiple summation. In the one-time case, one just put equal time a different location case. This summation is obtained using something like another meta methods or regarding it as some marginals of of, of some determinantal point process. But for this multi-time case, this multiple summation part is actually hard, or not that hard, but it's done by Johansson-Rahman essentially. And then one goes through what do I do? The result the formulas obtained after the summation is not suitable for asymptotic analysis. So one need to massage it through some orthogonalization procedure get something that's suitable to do asymptotics, and that corresponds typically to a Fredholm determinant. And after one obtained Fredholm determinant by some standard steep descent analysis, one should be able to take the 1, 2, 3 scaling limit. This basically this fourth step is adapted achieved by the work of Johansson and Rahman. So they obtained some formula of very similar type as the one I presented here for the homogeneous case and 2 times for the inhomogeneous case. But the Fredholm determinant of takes a different form, and a priori I don't know how to verify they are equivalent. So the what should I say? The way we are dealing with this problem is actually going in this direction. It's kind of a little bit weird. But what's happening is we are solving the corresponding problem of on the periodic domains that's found in the infinite line. There are analogs of the transition probability formula, and you can do similar multiple summation and orthogonalization. But after that, you obtain some Fredholm determinant formula for the joint distribution of the periodic model. And then what you do is you take the period large. What happens is if you take the period large, it reduces to a formula for the full space model. But what happened is it reduces to a similar different formula as the one in the format of Johansson and Rahman. But for that formula, that's the one I just showed you, and one can perform similar asymptotic analysis. So the advantage of working on periodic models is basically this step and this step, in my opinion, is significantly easier. And the final formula, in my opinion, is also easier, but I'm not sure. It depends on who you ask this question to. So that's really explained in what should I say, in the diagram. Of course, there are lots of steps here, and I need to explain to you at least some of the steps. I don't have that many times, but I guess I can explain to you what's happening for this step and maybe this step. There are some interesting combinatorics there. So maybe it's first to explain this to experts, because I really want to ask some questions about symmetric functions. That's really the purpose I want to explain this thing. So first, I'll explain this step. That is why one can see the full space formula from the periodic model at the very basic level of the transition probability. So at this moment, we are considering the variant of the previous model, and the only constraint here is we are considering the same inhomogeneous TASEP dynamic, that is the ice particle and the ice black particle and J's white particle exchange location with the rate pi plus pi j hat. But for the periodic model, there is an extra constraint, that is the first particle cannot jump to it's blocked by the last particle as well. So the natural configuration space is the usual configuration space for TASEP with this additional constraint. And this is the reason why everything is discrete instead of continuous. And here is a formula. It's essentially a analog of the Schur formula for the transition probability of TASEP. It looks like this. Consider two arbitrary configurations in the configuration space. The transition probability of going from y to x is given by this contour integrals with respect to z, and the integrand is given by some determinant. So if you're familiar with Schur's formula, you see this thing does not appear in Schur's formula. And another difference is here you have a discrete sum. And if you compare it with Schur's formula, you have the entries are given by continuous contour integrals. So that's the only two difference of this form of this periodic analog with the continuous with the full space Schur formula for transition probability. Of course, it is written should only write down for the homogeneous one, and I don't know if this two sets of parameters transition probability has been written down anywhere else. But anyway, it should be some folklore to experts. And what are the entries of this determinant? It's basically there are two parts of the entry. One is the crucial part, Fij, which I wrote down here, and it's if you compare it with the full space transition probability, it appears there as well. There is an extra factor one to multiply, and that extra factor JW is basically given by this QW divided by Q prime of W. It really hinges you to try to recognize this as some residues if you want. What is this Q? This Q is a polynomial in W, look like this, very natural, encodes basically those inhomogeneity. And this discrete set SZ consists of all solutions of the polynomial equation QW equals Z with some complex parameter Z that's the only place where this Z appears in this determinant. So that's it. So I'll explain what should I say? One slide explain how you obtain the Schur's formula from this one. So this is for the transition probability of the periodic model, but it reduced to the Schur's formula if you take L large but finite. That's very important. I'm not sending L to infinity, so everything is due to the algebraic property. And or how do I see that? So what's happening is this stuff really hinges you. It's of a type of one picking residues at those points where QW equals to Z. So you really want to integrate, replace this sum by some integral where this JW is replaced by basically QW over QW minus Z. By residue theorem, you have this equality, but you need to carefully choose the contour. A priori, this integrand can have, if you look at the form of your Fij, they could have powers at QW equals Z or at all the powers for this Fij, which are precisely those points negative pi hat L. But luckily, this QW has zeros at those points minus pi L hat. So if your QW has a large enough degree, which means you are picking your L to be large enough, and your X are fixed, then those powers are canceled by the zeros of the QW. So the only powers of this integrand would be at those points where QW equals Z, and you can choose this contour to be any contours surrounding all these roots, say a large circle. So at that for those cases, you have this equality by residue theorem. Then you plug in back to the determinant formula I just gave to you, and the result is something like this. You have a determinant with whose entries are given by contour integrals, and there is this extra outer contour integrals in Z. But now you recognize that the right hand side is actually analytic in Z at 0. Ignore those 1 over Z factor. The thing in the determinant is analytic in Z. So by deforming the Z contour to 0, you get basically this factor disappears. It's 1 because now Z is 0, and there's no discrete nature. You exactly get the continuous contour contour integral for the entry, and this is precisely Schur's formula. So this is a, what should I say, the simplest level of how one derives the full space formula from the periodic periodic formula. maybe a little bit too overly simplified, but that's what's happened. Probabilistically, it just means when you fix the finite location and you're only looking at finite time distribution, if you take the period really large, then there's no difference of looking at the what should I say, a periodic model or a infinite or a full space model, because particles just do not fill the boundary of this period. Algebraically, this is something like this. So that's maybe an explanation of what's happening in this part of the diagram. What's maybe to me maybe more interesting is how this multiple summation works for this periodic case. As I said, it's easier than the full space case because there is no ordering. So you can organize the sum, exchange the order of the sum in any way you like, essentially. So precisely how this works. So I'm interested in this type of multi-time joint distribution, and it's obtained by taking a multiple sum of the transition probability at each time step, essentially, where this sum is basically taking over all the possible configurations satisfying the constraint here. And then if you look at the transition probability, you can split this determinant whose entries are given by the sum as the sum of product of determinants using Binet-Cauchy formula. And the determinants appearing there turns out to be it's essentially the left and right eigenvectors, which I would call phi L and phi R essentially. And you can write in this way. Then you plug in this back to this huge sum, and then you try to perform this sum. This sum reduces to basically a two-body sum of the type summation phi xl w phi xr w prime. Lots of sum of this type. So really, one only need to figure out what this single sum is, or what this single type of sum is. And turns out those eigenvectors, as maybe well known to some of the audience, give eigenvectors some Grothendieck-like polynomial. Here, because of the homogeneity, this eigenvectors depends on these two parameters, pi I and pi I hat, and they take the following form, where the entries of one is more or less the reciprocal of the other. And this is some inhomogeneous analog of the Grothendieck polynomial. I tried to search literature very hard, but I couldn't find something of this type of generally written down in the literature. So I don't know if there is some more proper name of it. But what's happening is you take, as usual, you take pi L to be all zero and pi L hat to be all one. Then this is precisely the Grothendieck polynomial. Or maybe it can also be called spin Schur polynomial because it's the Schur degeneration of spin whole Littlewood, essentially. So, in the calculation, one needs the following Cauchy type summation identity. Here, because you are living in a finite volume space, I need this finite sum Cauchy identity, where I restrict my partition to be between any integer a, b. This is not really partition, some signature or whatever. It can be negative, and the product is understood by taking reciprocal when you are going in the backwards. But essentially, what's happening is if you take the usual type sum in the Cauchy identity, you get some kind of generalized Cauchy determinant on the right hand side. And the special case is where you send a goes to infinity, and assuming this vj plus pi l hat over wi plus pi l hat is less than one, you really get some general in Cauchy identity. And I did not know whether this guy appeared in the literature before or not. Actually, I didn't even know that the Grothendieck polynomial when I tried to do this calculation by myself. And but once things are done, I tried to search, and then I saw for the homogeneous case, when pi is 0 and pi j hat are 1, this type of finite sum Cauchy identity for the homogeneous Grothendieck polynomial was done in the work of Montague and Sakai, using the connection to some integral 5 vertex model. It's then some integer curving type calculation. For me, I just did this by brute force essentially. And that's it. And for the periodic case, maybe just one concluding remark. If you assume further that your spectral parameter W and Z satisfy some beta equation, which is natural in this periodic case, then the generalized Cauchy identity, the Cauchy determinant here, reduces to a general Cauchy determinant. And it turns out the original huge sum when you compare when you compute the what should I say this multi-time distribution becomes a huge sum over lots of product of Cauchy determinant. That's what's happening. I guess that's all the technical things I want to say. And to conclude, maybe in summary, what we have shown is a formula for the multi-time distribution of inhomogeneous TASEP depending on two sets of parameters, first for periodic models and then for full space model. And we take large time asymptotic analysis for step and show condition, assuming there are several assuming a finite rank perturbation of the homogeneous model. And the multiple summation involves some non-trivial combinatorics of Grothendieck-like polynomials, which if the audience know more, I'm sure some of the audience know much more than that. So some questions I have or I'm thinking about. The first one is the relationship of to the formula of Johansson-Rahman. So if you go back to this diagram, what's happened is before the orthogonalization, I can prove that my formula actually agrees with the formula of Johansson-Rahman before the orthogonalization. So at the level of counter integrals of n by n determinants, the two are precisely the same. So after the orthogonalization, they should also be same because orthogonalization doesn't change the determinant. But I just don't know why the two Fredholm determinants should be the same. Another thing is things I mentioned, but I didn't show you the formula works for general integral condition, at least at the finite time level. And there's one tiny little block of the matrix kernel wanting to change, and that change is also related to Grothendieck polynomial. It basically encodes the information of the initial data. For step initial data, that part is essentially a Cauchy determinant. So or maybe it's basically that part degenerate to 1 essentially. But in general, it's expressed by some Grothendieck polynomial type thing in terms of the initial data. So there's some hope one can massage this and understand the general large time asymptotic analysis, asymptotic. Or maybe something more important or maybe more interesting to some of the audiences, what happens for ASAP. So here I'm discussing primary determinantal thing. So really for ASAP, I believe things should be parallel, except that instead of seeing this Grothendieck type thing, one should see some spin whole little, some spin whole little. But I just couldn't find a Cauchy identity for in the existing literature for spin Hollywood that degenerates properly to the one have at this moment for when SN Q goes to 0. Maybe if the audience know something like this.
Yes, I have a paper on that.
I see.
So you can check.
Why need some refinement of the Cauchy identity?
Refined Cauchy for spin Hollywood. Yes.
Yeah. So then I'm glad.
And check it out. It is almost the same as for the Hollydoods, but there are some parameters around, and for ASEP, there is a determinantal summation formula for ASEP.
All right, then that's all I want to say today. And thanks a lot.
Okay. Thank you very much. Let's